Hello, in this video we're going to look at the Gram-Schmidt orthogonalization process from a projection matrix standpoint. I have a video called Perpendicular Projection Matrices, and that's kind of a precursor to this, and if you haven't seen that video, I'd recommend watching it before this. And also, if you're only interested in the Gram-Schmidt algorithm, you could probably just fast forward to page 4 and get right to it, or just wait for the next video where we go through this in R. We take these algorithms, actually 3 different algorithms, and run them all through the R statistical software. So here in this video, we had 7 properties, P1 through P7 of projection matrices, and P1 was the definition. So if M is a perpendicular projection matrix, PPM, onto the column space, and the C stands for column space of X. Some call this the range of X, but I think of it as the column space of X. If and only if this is the case. For every vector in the column space of X, M times V, you get V back. So it projects it right back onto itself. W is in the orthogonal complement of the column space of X. Then M times W, you get the 0 matrix. They're perpendicular to each other. So the first property here, I'm going to call it P8 because we ended with P7 in this video. P8 is a follow-up to P5 and in the previous video. So let O be an orthonormal basis for the column space of X. And so these are R linearly independent vectors in by one vectors, and they span the column space of X. And let W be another orthonormal basis for the column space of X. Then O transpose, W transpose are the same. Now, from P5, and it's a follow-up to P5, we know that O transpose and W transpose are perpendicular projection matrices onto the column space of X. We proved that in that video, the previous video. So now let P4 be by P4, the perpendicular projection matrices are unique. And so since they both project onto the same column space, they have to be the same. So they're equal. Now, the reason I'm showing you this property here is in the Gram-Schmidt orthogonalization process, we create orthonormal basis. So we have a matrix X, so there's R, vectors, column vectors, and then we run it through the Gram-Schmidt process and we get O, which is an orthonormal basis or orthonormal vectors for this matrix X. Okay, it is absolutely not unique. However, the perpendicular projection matrix generated O transpose is unique. Okay, and so I'm going to start a series on multiple linear regression from a perpendicular from a projection matrix standpoint, and we'll use the Gram-Schmidt process to generate an orthonormal basis, and then we'll create a perpendicular projection matrix from it. And then, even though the orthogonal basis is not unique, the perpendicular projection matrix is unique. Okay, so the next property, P9. X transpose X, generalized inverse X transpose. Now this generalized inverse can be replaced with an inverse, and that's if the columns of X are full column rank. But if not, then we have to use a generalized inverse. I have a video called Generalized Inverse if you want to watch that. So this is a perpendicular projection matrix on the column space of X. So the proof is we need to show that P1 holds. So let's let V be in the column space of X. And that means we can write V as this X times B, where B is some vector, right? It's in the column space of X. So then we have this matrix, which is often called the hat matrix in multiple linear regression, times V. So we replace what V is, XB. Well, then this right here is the, it's equal to X. And so we get X back, XB, and then we get V. Now the reason that this is X is from Theorem 3 in a video that I put out called Generalized Inverse for a Symmetric Matrix. Okay, so that's why this property holds. Let's let W be in the orthogonal complement of the column space of X. Then this hat matrix here times W is 0. And if you think about it, this X transpose took the columns and made them rows. So then when we're multiplying each row times W, they're orthogonal to each other, so that dot product is 0. So then this creates a vector of zeros. And so we're proven. So that is a perpendicular projection matrix onto the column space of X. And so this right here, so if this is a vector of 1, so an n by 1 vector, then this becomes a perpendicular projection matrix on the column space of 1. And of course, the capital 1, if that's such a thing, capital 1 versus lowercase 1. Capital 1 is n by 1. And it's proof by P9. We showed that is. Now, the reason that's important, in multiple regression, the data matrix contains a column of 1s corresponding to that intercept parameter, which means that the column space of 1 is a subset of the column space of X. And then that becomes important for, well, if you watch that first video, that's really important. And then here's an illustration of what's going on. And this becomes important, you know, these properties here in the Gram-Schmidt process. So note that the identity matrix, n by n identity matrix, is a perpendicular projection matrix onto the n space, and OO prime is a perpendicular projection matrix onto the column space of X, where O is the orthonormal basis for column space of X. X is an n by R matrix, and then since this column space is a subset of the n space, then by P6 in the first video, the identity matrix minus OO prime is a perpendicular projection matrix onto the column space of this, the identity minus OO transpose. And here's a big note that by P7 in the previous video, if we have an X in this column space, then X is a member of Rn, which is this one, and it's in the orthogonal complement of the column space of X, which is this. So it's in the orthogonal complement of this. And so that plays a super critical point in the Gram-Schmidt process. So we have follow-up to example 1, and then we're going to have follow-up example 2, where we give some numbers very quickly. So let's let X be a matrix with 2 columns, and let it be X1 and X2 here. So now notice that those are already orthonormal to each other, and if you think about them in columns, then, and what this spans is the X1, X2 plane, because X0, or the X3, or this third component, is 0. So these span the X1, X2 surface, and although I call them X1 and X2. So the first component, second component. So X is a 3 by 2 matrix. Then since they're orthonormal, right, then this becomes a perpendicular projection matrix. So X transpose, which is this, okay? So here is the cool thing about projection matrices. So any vector that we pick in 3 space and pre-multiply it by this, it projects it down onto the column space of X, which is it's sort of the X1, X2, or the XY plane, or however you think about it, because Z is always 0. Now if we look at I minus X transpose, then it's easily seen to be this, where it's just a 1 in that last component. Now this is This projects things onto the orthogonal complement to the column space of X with respect to X3, or 3 space. So let's let W be in this column space. So that means W can be represented like this. So this projection matrix, or this column space, times B. But we know this is this, so when you multiply that, you just get 0, 0, B3. And this is for any B in R3 space. So then, if we let W be in R3 space, then, and it's in the orthogonal complement space. No, this is not coming out right. So this B is in R3, so then W in 3 space, and that, that just by definition, and if it's 0, then it's in the orthogonal complement space of X. Okay, so that was kind of a little difficult there, but let's go through a specific example. So let's let X3 be any vector in 3 space. Okay, so then if we take this matrix times P3, it's going to project it down onto the column space of this, which is 0, 0, 3, right? If you do that multiplication, which is an element of this column space. If we take the projection matrix XX transpose and pre-multiply that to X3, then we get 1, 2, 0, which is in the column space of X. Okay. Now follow me here. It's a little monotonous here, but it's going to really help when we cover the Gram-Schmidt process. Now notice that X3 is actually the addition of these two components here, right? And this one lives in, if we call them V1 and V2, this component lives in the column space of X, and this one lives in the orthogonal complement to the column space of X. Okay, and that plays a part here. So let's jump right into the Gram-Schmidt. Gram-Schmidt orthogonalization procedure using projection matrices. Okay, so here's the general steps for the Gram-Schmidt procedure. We start with R n by 1 vectors. Okay, right here, and they're linearly independent. Now we transform X into orthogonal vectors, Y, and then we transform Y into orthonormal vectors. That's the normal procedure for this. Okay, but here's some notes before we get to page 4, which is very simple steps for the GS procedure. OO transpose. Remember, this is where these are orthogonal or orthonormal bases. O is this, and then the transpose can be right. You transpose it like that, and they become rows. But then when you multiply this out, you get this sum, right? And then this can generically be written as the sum of these OI transpose. So, and the reason I'm showing you this, in most references you see it written like this, as opposed to just this matrix product. Okay, I think it's cleaner to write it like this, but you'll always see it like that. I is a perpendicular projection onto Rn space. OO prime is a perpendicular projection on the column space of X, right, with all our columns. But if we take away some columns, say where we only have I columns, not R, right? And then we create an orthonormal basis, and we're going to call that OI, and I is in parentheses, OI transpose. Then it's the perpendicular projection matrix onto the column space that's spanned by the, just the I columns, and where this is, of course, an orthonormal basis. Well, O is the orthonormal basis for this column space. Okay, so by P7, we know that O, or I minus O transpose, is a perpendicular projection matrix onto the orthogonal complement space of X with respect to Rn. And this is OI prime transpose is orthogonal. It's a perpendicular projection matrix onto this column space, or the orthogonal complement of this column space with respect to Xn. Okay, so with that background, this is the one-step Gram-Schmidt algorithm. This is it. So yi plus is I minus, and these are the orthonormal basis for the the first I columns times xi plus 1, and then we normalize it. Normalize it to 1. Okay. So if we on step 1, so y1, it's I minus the first, it's 1 less, so the first 0 column, so it's nothing. So it's just I, and then take it times x1. So y1 is x1, and then we normalize it, so it's a length of 1. Now at step 2, y2 is I minus the first column, times x1. Now notice though, so this takes this vector and maps it to the orthogonal complement space of O1, which is x1. So then y2 becomes orthogonal to y1, right? Because it mapped it onto orthogonal complement. Now then we normalize it, just make it length 1, and we keep going. So I equals 3, so y3 is equal to this, I minus O2 prime. So this is a perpendicular projection matrix onto the orthogonal complement of the first 2 columns of X, right? And then then x3 comes in, but it's orthogonal to the first 2 columns of x2, but the first 2 columns were orthogonal, so now all 3 of them are orthogonal, and then we normalize it. Well, we just keep going until we get to the rth vector or rth column. We take it times this perpendicular projection matrix, so this is orthogonal to the first r minus 1 columns of X. And then we get R, and then we normalize it, and we're done. Okay. So the next video will be an R program implementing this algorithm. And also there's 2 algorithms that I noticed on Wikipedia that are worth going over too in this R program. Well, I hope you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.